I'm not going to be very systematic. We're just going to kind of write down some integrals and play with them. And then later on in the lecture and next week, we'll treat things in a much more systematic fashion. And show how you can use counter terms to prove a theorem. So we were looking at the phi cubed theory on Rn. This Lagrangian. And we were studying the one-loop Feynman diagrams. Which will be part of computing this path integral. Bar, sin phi, and zero. So where we had this background field phi 0, which was only in the interacting term. And if we take the logarithm, bring us to looking at connected diagrams, we saw that this had a diagrammatic expansion. The first term was phi 0 cubed over 6. And then there was more tree-level terms. And then there was an order h bar term. These were the first two order h bar terms, and then there was, of course, more terms. And what we saw was that this diagram here, this is divergent. And if we let the propagator be the integral from t equals 0 to infinity of the heat kernel, t minus n over 2, t minus So, I mean, to see the divergence, we introduced this representation of the propagator and its regularized version. And we saw that if we took this diagram with the regularized propagator, and here I had this field phi 0 on this external leg, the answer was, well, since this edge goes from a vertex to itself, I'm just going to be evaluating this when x is equal to x prime. So this factor just drops out. So equals epsilon L e minus n over 2 dt integral x by 0 of x. Okay. So our goal today is to analyze counter terms. So for these diagrams, what we're going to see is that we can write the diagram as a sum of two pieces, one of which converges, and one of which looks like a Lagrangian. In this case, things are particularly simple. It'll be more complicated when we look at the next diagram. So here, we can make this converge. Or have a limit as epsilon goes to 0, we introduce a counter term. I'll write it like this, I, 1, 1. This means it's one loop and one external line. And this counter term is just going to be the singular part of this guy as epsilon goes to 0. Now, what does that mean? This is super simple. It's just an integral. I mean, it's super simple because it splits as a product of two integrals, which will not normally happen. So the integral over t will just produce t, the 1 minus n over 2. So the counter term should, given the lower bound, so the counter term should be 1 over 1 minus n over 2 epsilon to the 1 minus n. And then, obviously, the amplitude with this regularized propagator minus the counter term has an epsilon to 0 limit and this limit is defined to be the renormalized amplitude.
Kevin?
Yeah?
Small question. So you're introducing a counter term that is not originally in the diagram, right?
Yes.
So
that always happens. Don't believe this.
Okay, now. I guess the question is, if you had introduced a term of linear order in 5, do you still need to do this or not? Or is there a chance that this diagram does not contribute at all?
If you had introduced, no, if you no, because this is at order h bar, so it can be cancelled by an order h bar term. But I think you're thinking of like a kind of subtle conceptual issue, which we'll come back to later. It turns out that at least at most of the time, the counter terms are fixed uniquely by the condition that they must cancel the singularities. So then it doesn't matter if they don't appear the original Lagrangian. There's no parameter. It's not like you're introducing some more free parameters that just fixed uniquely. Sometimes, though, if n was 2, then this would be logarithmic, and then the counter term would not be fixed uniquely because I couldn't really distinguish between log epsilon and log 2 epsilon with the same singularity. So when at one loop, when I have a logarithmic counter term, that's not fixed uniquely, and so it should look like something that appears in the Lagrangian. Or at least. So we'll discuss that more in detail later. So here we're just kind of being a bit mechanical about it. Okay. Yeah. Mm-hmm. Yeah, okay, so let's elaborate. That's a good. So you want your counter term to be a function of epsilon, which is somehow singular, because we're doing like a minimal subtraction scheme, and it's clear that like 1 over epsilon is singular, 1 over epsilon plus 1 is not, right? However, log epsilon, you don't really know if log epsilon or log epsilon plus 1 is singular. That's an arbitrary distinction. Go from one to the other by scaling epsilon. So, does that answer your?
Yeah.
I mean, you could have crazily decided to choose that like, I want my purely singular functions to be 1 over epsilon plus 1. That's just a bit unreasonable.
Sure.
You mean, like in the MS bar traction, you have the freedom to include more terms in the counter term, so that well, the counter term isn't unique, and so you can choose the MS bar.
Well, so the counter terms are. I wanted to prove a theorem at the end of the lecture today that the counter terms are unique once you decide what it means for a function of epsilon to be purely singular. But that's a choice you must make. But that choice in particular fixes a scale, because it tells you that log epsilon is singular, but log 2 epsilon is not purely singular. So is that? And I've decided to make the reasonable choice that, 1 over epsilon to the n is purely singular. I don't. It would be crazy to do something else. So let's look at the next counter term. So maybe I'm doing the lecture in a kind of backwards order. Like I should have maybe discussed these conceptual issues first. But I wanted to just kind of look a little bit at the mechanics of the integrals, see how to figure out what are the singular parts. So once I've regularized, this becomes x2 T1, T2 to the minus n over 2 by 0 of x1 by 0 x2 e to minus 1 over t1 plus 1 over t2 x1 minus x2 squared. So what I want to claim is that this can be written as a sum of two terms. A term with a well-defined epsilon to 0 limit plus a finite sum of terms which are functions of epsilon times integrals of times Lagrangians, integrals only over one x variable, not of two x variables. So something like this, phi 0 of x, some derivative, differential operator of some kind. It's going to be some little passing of some power. Okay. Now this decomposition into sums of things like this and things like this is not unique, because I can take some terms here and move them over here. But it is unique as long as I decide that these guys are purely singular functions of x. This is unique. If these f I of epsilon are purely singular. So I make a choice. I look at all the functions that can appear, and I say some of these functions I declare to be purely singular, and the other ones are the regular ones. And of course, my choice is the only functions that can appear in one loop are epsilon to the k and epsilon to the k log epsilon. And I want to say if k is less than 0, and k is less than or equal to 0, these are the purely singular ones. At higher loops, you'll find much more complicated functions like polylogarithms. At one loop, things are easy. What's that?
Log apps.
That doesn't appear at one loop. It can appear at higher loops, I think. But at one loop, you only find log. I think that should be clear from the momentum space description, where there's just a single integral, because there's one loop. Mm-hmm.
Principle, it's possible for the counter term that we added here to affect which diagrams we should be counting for this computation.
That's an excellent question. For this particular, like the counter term we've added here, will affect what will happen at two loops. But it actually won't affect this particular one. I can see that you can think of like taking this diagram and
Yeah, basically.
but that actually doesn't affect things because this is a tree and doesn't introduce any more singularities.
Okay, so it's
So it turns out that the k-loop counter terms can only affect things at higher loops.
which counter terms?
So if you're a k-loop going higher. Okay, so let's see. Probably there's easier ways to do this. This kind of way of breaking it up into a thing which behaves well and a thing which is a Lagrangian. But the way I want to do it works well on any manifold, so which is why I want to do it this way. So how are we going to do this? So what we're going to do is, firstly, we're going to integrate over x1 minus x2 in the normal direction. And then you see the integrand, it's a Gaussian integral. So as long as this thing appearing here is small, it can be expanded over things which only live at x1 is equal to x2. We get an expansion in series in this quantity. After finitely many terms in that expansion, we'll get something which is a well-defined epsilon to 0 limit away. So let's see how to do that. Concretely, let's just remind ourselves of to do Gaussian integrals. So we did this in the first lecture, but I was lazy and I absorbed some factors into the measure. So let's do it including the correct factors.
Sir,
Yeah.
what you know that every why do you take every propagator to have the same epsilon and L?
I think it has a meaning because it's certainly much more convenient. You don't buy anything by having more epsilon parameters. Maybe I can postpone the physical thinking about the mathematical meaning of that later.
Just you can use different epsilons and L's, but then you have huge number of regulators for this theory. Right? But basically what you're trying to do is to get rid of short distance physics, which the claim, I guess, would be that if you do it with a single regulator, it works. More regulators. So think it like in a physical system that short distance is the lattice constant, for instance. And that is sort of like unique or a single one. That should work with regular frequency. But I guess in principle you can use as many epsilons and L's as you want.
I mean, maybe the answer I would give in some period in the future would be that these diagrams have some homotopical interpretation, where you're relating things with a differential depending on epsilon and another differential depending on L. So it's only when they're all the same does it have this nice homotopic interpretation. Okay. So let's go back to very basic integration. So first thing is that there's this factor of s to the n over 2. And the leading term is the value at 0. The next term is like s times Laplacian at 0 plus s squared over 2 Laplacian squared x at 0 plus. So if we look at this integral, we let y be x1 minus x2 say over 2. And x is like x1 plus x2 over 2. So this integral becomes just integrating the integral integral over the ti, integral over x, integral over y, p1, p2, n over 2, e minus 1 over s y squared, phi 0 x plus y, phi 0 x minus y, where s is t1 plus t2 over t1, t2. Now, we plug this in to the formula for the Gaussian integral. We integrate over y, we'll find an expanding in s. This is equal to the integral over the ti, integral over x, t1, t2, the n over 2, t1 plus t2, n over 2 over t1, t2. Are you doing something wrong? Oh, I feel these factors aren't right. Now that's a minus n. Now this is the other way. S is this, sorry. Okay, sorry about that. Okay, sorry, so now I got the S's and the something wrong, but now we plug in S to the n over 2, and the factor of T1, T2 to the n over 2 cancels, and we're just left with 1 over T1 plus T2, the n over 2, times the series expansion we get from a Gaussian integral. So the first term is phi 0 x squared. The next term is Laplacian in y, phi 0 x plus y, phi 0 x minus y. And this comes with some factor of great. So now the important thing to note about this series is that each term in this series is the integral of a local quantity just over x. So each term in this series is a Lagrangian. So we've completely gotten rid of the non-local piece, the integral over y, and it's been replaced by an infinite sum. Further, as we go out in this series, we get higher degree polynomials in T1 and T2, so it becomes more and more convergent. The integral over the t's becomes more convergent the further you go out.
In both L and epsilon, or?
Just in epsilon.
And we have heard about the...
No. We could introduce a mass to deal with the I/O regulator. It could be on a compact manifold. Not too worried. So if you stare at this formula, you'll realize like how many terms do I need to have to make it convergent? Something like this term here is of dimension 2 minus n over 2, and each term here is of dimension 1. Oh, so you need something like, I don't know, n over 2 minus 1 terms will be divergent. And then the rest will be convergent. So now we've achieved our goal. We just look at the first some number of terms, this expansion. That's the divergent part. And we throw away the rest because that's convergent. And we're happy because with the first some number of terms, each always involves the integral of a local quantity just over x. Okay, questions? So let's, just to be really concrete, let's just take n is 4.
Sure.
Yeah,
So going back to the x, I was imagining like the diagram like it's a triangular vertex, but with like the counter term and eating on the same edges. So it would look like
Yeah. I know what you mean. Like, so it's like this kind of genus 1 vertex, like that.
yeah, exactly.
And then so that does play a role, and that will cancel the singularity in this one loop diagram.
Okay. But it doesn't appear.
But it doesn't, like, there's another singularity from this diagram, but they're kind of independent. So if we're going to be really concrete, we take n equals 4, and number 2 is 2. So this quantity here, because there's a 2 on the top and a 2 on the bottom, looks logarithmically divergent, but the next term is convergent already. So when n is 4, you only see one term, like one divergent term. Which is the integral of pi epsilon to L by 0 x. And this singular part of this is easily seen to be proportional to the log of epsilon. This log epsilon square plus something which is non-singular. So in this case, we find the one-loop counter term is log epsilon by 0 x.
Okay.
Yeah.
Confused about something. So this essentially the correction to the mass of the propagator, right? Should then it come with some inverse length scale or some mass scale?
Well, we're doing something funny because I decided to just study the phi cube theory. This was the phi 4 theory.
Oh, okay.
The same analysis would have applied to this diagram. It would have been a phi 4. So in a phi cube theory, dimension of phi is phi.
But epsilon itself is a dimension of 2.
What's that?
Epsilon itself is a dimension of 2.
Yes, epsilon is dimensional. Log epsilon, on the other hand,
So
not dimensional, right?
should we also include the scale of m just to say that log epsilon is going to
No, I would.
You can feed that into the finite. Yeah, they log epsilon over m.
Yes.
Log n into the finite.
Okay. So one can imagine this proceeding for all diagrams, and indeed it does. So we'll get to that in a little bit. So I mentioned at the beginning that this works nicely on any manifold, and that's a kind of nice feature of this space-time approach as opposed to the Fourier space approach. And the reason is very simple. Because the heat kernel on any manifold, the details are a little subtle, but it has a nice expansion when t goes to 0 in Riemann normal coordinates. So this looks like heat minus n over 2, I mean, both the usual factors of pi I'm not caring about. And it has a nice expansion, which is the flat space heat kernel times a series in T. So we can just do the same arguments by plugging this expansion in. And the main point is that we will always have this Gaussian factor, so that the integrals, we will always be able to do these Gaussian integrals in the same way.
So these FRs, the single derivative, I mean the functions?
As in functions of curvature.
Yeah, they're actually, let's see. I don't remember the details, but like, sorry. For instance, you can say like these functions are particularly nice when you look at them on the diagonal, next equal x prime, and they have some nice expression in terms of the characteristic classes and the curvature and so on. So this is how one proves the kernel proof the index theorem. But I think if you look at these functions in general, they're kind of a big mess, and nobody knows a good formula for them. I mean, it's actually super fun to use this because you can think of like, if you look at this tadpole diagram on a manifold, then you're putting the kernel when x is equal to x prime, and you're just extracting off this. So you can immediately see things like anomalies are related to the curvature. Okay, so how about at higher loops? How are things going to work? So this gets back to the question Eugene asked a few minutes ago about like how, you know, if I introduce a counter term at one loop with a certain number of external lines, this might affect what happens further on. And it does. But it turns out that there's an inductive construction of counter terms, and that the counter terms are just uniquely fixed by the requirement that they're singular. So here's the theorem. Well, first let me introduce some notation. So if I is any Lagrangian, which is say cubic, well, we think of this as being the interaction term. And we're just working with a single scalar field, then we can consider we let quantity I'll call W is h bar log e h bar. So it's this operation we were doing which builds the Feynman diagrams. So it has this concise expression where this is some way of contracting, like we discussed before, but in concrete terms, this is sum over connected diagrams plus external lines h bar to the number of loops of gamma times the Feynman amplitude. So here, this is the propagator. This is the interaction. And this is the external field, or background field, which lives on the external lines. So this is just the same thing we've been doing before. I've just introduced notation to describe this series. What's that, sorry?
L gamma was the number of external lines.
No, sorry, the number of loops, so the first byte number. is that for any Lagrangian I, there exists a unique set of counterterms such that that each order of h bar you want this to be a sum, finite sum of functions of epsilon and Lagrangians. These are purely singular functions. And these are, this is a Lagrangian. And the main condition is that the limit exists.
Do you want to require I to be at least cube modulo h bar?
Yes. Otherwise, this sum doesn't.
So is that about like finiteness of the sum?
Yeah, of the sum of the Feynman diagrams. So, like, you want at each you want I to be at least cubic in h bar, cubic modulo h bar. Otherwise, you can kind of have Feynman diagrams which are like infinitely long strings. It doesn't converge.
For the sum, for the expression for counterterms, do we require that sum to be finite?
At each order in h bar, it's finite.
At each order in h bar, it's finite.
But as you go further on, there might be longer and longer. Yeah. Actually, to be super careful, at each order in h bar and at each order as a polynomial of phi. So we've already kind of seen how this works for the first couple of terms for the one-loop diagrams, because we saw we can write the amplitude as a sum of something which has a nice limit and something which is a Lagrangian. So the general proof is like kind of the same, just more involved. So let me any questions? So let me like try and explain how you do this. So here's the proof. So we let W sub ik be the term which is h bar to the I times a polynomial in phi 0 of degree k. So essentially, this means the piece coming from diagrams with I loops and k external lines. I say essentially because it can happen that I has some h bar dependence. So we have to, when we count the loop number, we have to be careful that the vertices might themselves have a loop number. Now, suppose we have constructed counter terms I or S, which are basically, again, h bar to the or and polynomial of degree S in the field for all or less than I, and when or is equal to I, S less than K. So we're going to assume this by induction, and then we're going to construct the counter term at the next order. So we consider this guy. Evaluate an I minus the counter terms we already have.
That sum also include R equals I?
Yeah, the or equals I part is over here.
Oh,
It's like, or this is the or equals I, and that's less than K. So like these are the ones we already have. So the first step, one, is to show, yeah,
Is S being summed over in that first sum?
0 to infinity. So there's some kind of partial order in the set of two indices I'm using. So step one is to show that this guy has a nice small epsilon asymptotic expansion. So we do this by doing the same thing we did before, except it's much more complicated. So we say, well, this is a sum over diagrams. Each diagram each diagram we get some big Gaussian integral, and then we apply Wick's lemma to get a nice asymptotic expansion of that Gaussian integral. Step 2. Well, we take the terms in this expansion which are purely singular, as a function of epsilon. And these are going to be our new counter terms. Well, a priori, we don't know that what this guy gives us some Lagrangian. So we have to check that this piece will be local, some integral of just some local quantity. A priori, it's going to be integral over a bunch of copies of the manifold. We need to check this is local. And here's the key trick. Let me give this quantity a name. This is some Fik times an epsilon L. So the key trick is that if I differentiate this guy with respect to L, this is non-singular. Epsilon goes to 0. So the reason is, so this is what makes kind of the key point that allows us to guarantee everything is local. So if I differentiate it, what do I find? Well, if I have some diagram, whatever it is, and I have some propagators, the only thing that depends on L is the propagator. So when I differentiate with respect to L, all I'm doing is replacing one propagator by its L derivative. So the L by the L, you replace 1 P epsilon L by, well, what's its L derivative? Which is, that's the heat kernel. And the heat kernel is smooth. And also independent of epsilon. So the derivative of this quantity is written as in terms of the quantities where the singularities have already been cancelled. So it looks like this. So there's one of a smaller loop number. With the heat kernel. So we get this sums, I take special edge, or the propagator is replaced by the heat kernel. Either it is a non-separating edge, in which case it looks like a diagram of lower loop number with this loop attached, or it's a separating edge, and there's a number of ways the loops on either side can be arranged, so I get a sum of terms. Now, by construction, I've inductively assumed I have the counter terms which make these guys and these guys all have a nice epsilon to 0 limit. All these terms okay. Now, so how does this help us? So we said we're going to take the singular part. What this tells us is that the singular part is independent of L. So that means I can just send L to 0. And when I send L to 0, the heat kernel decays very rapidly away from the diagonal, and I just get these local contributions. Because the heat kernel is some exponential e to the distance over t, and if t is only allowed to be very small, this decays super rapidly away from the diagonal.
Sending L to 0.
Yeah, because the singular term is independent of L, so I calculate it when L gets very small. You see, so the singular term has, so what we're seeing is that the singular term, for a fixed value of L, the singular term has decay away from the diagonal of this form, e to minus x squared over L, but it has this decay for all L. Therefore, it must just be 0 away from the diagonal. Singular part is independent L. So, which implies by sending L to 0, L to 0, it's local, i.e. the integral of a Lagrangian. Okay. So any questions about this argument? Yeah, I know we only kind of sketched it, but I mean, we saw this already actually. Like when we did this Gaussian integral, we kind of saw explicitly that the singular part is independent now.
Confused about sending L to 0, like from our physical perspective. It works to show that it's local, but at the end of the day, I guess you're thinking within large distance physics. But if you're sending L to 0,
So I think what's happening is you have to think about what. Right, suppose I take this normalized amplitude, and this is a function of epsilon. What's the interpretation? This is the effective action of the theory at some scale. Now we can choose to study the effective action of the theory at a very small scale. Yeah.
That equation with the output looks a lot like Lorentzi's equation.
It's the infinitesimal orgy flow equation.
Right.
Yes.
That's what I checked.
Yeah, absolutely. Yeah, because we're like, L is the scale, we're differentiating the amplitude of the scale.
so you cannot guarantee that the effective action is local for any L.
No, but it has nice, I mean, you don't expect it to be, but well, you can get some control over its decay. Right? It has like, for L small, it decays at a certain exponential rate. If I take my inputs to be well separated, it'll be decay. But only kind of asymptotically is it. Local. So I think we will stop here, and next time we'll treat things like maybe slightly more like axiomatically, and move on. Unless there's other questions.